I think we can start the class. Welcome to CS329A, Self-Improving AI Agents. This is the first iteration of this class. And Akanksha and I are co-teaching and have co-created this class. And we are very excited to learn about the best and the latest in AI and agentic optimization. A little bit of intro. I am a assistant professor of computer science here in the CS department. And Akanksha.
I have been in industry for the last decade doing LLMs, and this year I'm also a adjunct professor at Stanford, so I'm co-teaching with Azalia.
Yeah, and we are very lucky to have Akanksha here. She got her PhD at Stanford, and she has done so many amazing projects at Google, leading very big projects, including Palm, which was one of the best early large language models trained at Google, trained on multi-pod TPU. So we are. I'm very grateful for her to be here and to spend this quarter teaching this course. But we also have a couple TAs, Mert and John, which you're gonna hear more about them, and they're gonna announce their office hours and hopefully gonna be very helpful throughout the course. We have a website, you can check it out. There are a lot of information out there on the website, which I hope that you will take a time to review as you are kind of finalizing your decisions about the course. Okay, so today's lecture, there are two parts. In the first part, we are going to describe an overview of trends in LLM scaling, and we go over what we cover in this class. And the second part, we are going through the course logistics, and it's, again, very important for all of you to listen carefully here and review these materials. So let's start with the technical course overview. But before that, let's have a little bit of background on LLM scaling and why nowadays, or right now as we are speaking is a very exciting time to think about AI and agentic AI optimization. So a lot of you in this room, hopefully all of you, as assigned by the prereq for this course, have seen this graph or are familiar with the pre-training scaling laws for large language models. What this scaling laws suggest is that there is a power law relationship between LLMs test loss, which correlates with their capability, and the amount of compute that we use for training them, the number or the size of data sets for training, as well as the number of parameters in the model. So what this scaling laws is suggesting is that we can almost precisely predict how the test loss is going to go down as we throw in more compute without even increasing the compute. Before even doing so, we can predict where these models are going. And these have a lot of implications for how we approach AI optimization and performance. So given this observation that has continued to hold for many years now, they're up until 2024, and it might continue to exist, there has been exponential growth in the size of large language models. So since 2018 up until when GPT-4 came out, you can see this really magnificent increase in the power, in the size of the language models. We went from models that were barely 100 million parameters to GPT-4 size models that reportedly are in the size of hundreds of billion, if not trillion plus parameter sizes. So there is an exponential growth, and all of that made sense because the models keep getting better. So we are, and the companies keep being excited about spending much more compute and data on training the models to get better quality. Now, continued improvement with scaling is one exciting property, but that's not everything that we get as the models have become bigger. Another property is the emergent behavior, and those are the capabilities that only emerge in larger models. And here I'm going to show you some examples. So perhaps the most the first kind of emerging behavior that was very interesting to see in LLMs was the zero or few shot learning. So what we mean by zero shot learning is what is commonly we know as prompting the model and asking them, for example, asking the model to a question, and then the model knows how to answer it. This is perhaps very kind of like understood and very expected as you talk with ChatGPT or Gemini and so on. But this was not a kind of a built-in property of the models up until like a few years ago. So the zero-shot property is, for example, you can now ask the model to translate English to French, the following word cheese. And the model can do that and the model has not necessarily seen an example of translating English to French for cheese, like in this particular format, right? But the model has learned a lot through its pre-training and through its training process that it can mix and match things and it can generalize to new kind of setups. And that's what we can see with zero shot and few shot. Few shot is just extending the zero shot property, and which is interestingly improve the model ability to answer questions. And in this case, for example, for translating English to French, instead of just asking a question there, with few shot, you will show the model a few examples of what this translation means, and the model can leverage those to improve its quality of responses for the test question. Another emergent behavior is the chain of thought property, which also is a very powerful property of language models. What we mean by chain of thought is that instead of just prompting the model and asking it and showing some few shot examples, we can basically walk the model through the process of getting the results for these examples, and then the model can leverage that quote unquote chain of thought in order to solve newer problems better and at a with a higher success rate. So in this case, we have the problem: Roger has 5 tennis balls. He buys 2 more cans of tennis balls, and each can has 3 tennis balls. How many balls does he have now? Tennis balls. And the answer is 11 in this case, and that's a few shot, a one shot example. But it turns out if the model is also shown this process of how to get to 11, which is Roger started with 5 balls and 2 cans of 3 tennis balls, each is 6 tennis balls, and so on, and 5 plus 6 is 11. This is on its own is very useful for making the model know how to break down a problem and walk through the reasoning steps to answer a question. And interestingly, these kind of chain of thought kind of property, the ability of the model to learn from chain of thought, appeared more and more in larger models with larger parameter sizes, as you can see here in like models like Lambda, GPT, and Palm. As the model size increased and the model parameter size increased, the ability of solving GSM-8K problems, these are middle school math problems, increased as chain of thought reasoning was brought up in the prompting examples. And chain of thought is another emerging behavior for the language models is their ability to solve entirely new tasks. So in this problem, in this graph, you're seeing that for completely new types of tasks, like question answering in a different language, or like model arithmetics, these are the tasks that, again, models are not specifically trained on it, but they can generalize to that and they can solve that. And for all of these problems, again, up until maybe last year, or the most gains that we were seeing out of these models were coming from making the model larger, putting more data and compute into the pre-training, and getting a lot more performance out of them. So that was a big kind of push for increasing the capability of the models. Now, when ChatGPT launched in November 2022, it made a huge splash, right? It kind of was a kind of a very big moment for AI. And even before that, we still had large language models. They were still like you could have get certain capability from them. But what really made a difference here was that ChatGPT, it was instruction fine-tuned on the previous version of GPT, of the GPT 3.5. And what that means is that this model was really fine-tuned to follow instruction that is, and the kind of prompts that are asked by humans when they're asked. And this is a process on top of the pre-training that pretty much all the other models at the time were going through. Another kind of big difference or distinguishing factor for ChatGPT was that it had this dialogue format. It provided this interface to the public, to everybody, and it was fine-tuned with methods such as reinforcement learning with human feedback. And the responses were not only following the human instructions, but also they were designed to be helpful, harmless, and also to be sensible. Now, let's take a look at where these kind of optimizations come from in the process of optimizing LLMs. So in pre-training, it's just training on the next token prediction and continue just bring in as much as possible data, and ideally good data. But there is not a whole lot of focus on refining the data sets, or the training is pretty much on focus on next forward or next token prediction. But with fine tuning, there are a lot of new kind of features and new kind of optimizations that can go into the design and of the model. One of the things that we want during fine tuning is alignment of the models with human preferences. So AI alignment is the problem of kind of steering the AI models, to be aligned with the goals of humans, and to kind of like we want the AI to generate responses that are sensible and preferred by humans that use the AI. And this is, of course, one of the biggest challenges of AI. Even with the most capable AIs today, there are times that we ask the model that a question that might be very simple if you ask a human, but they still fail to answer them. Whereas the models can solve very, very complex problems. So there is still this challenge of AI alignment, and this is, but it turns out that we can make huge strides towards this alignment by fine-tuning the model to be aligned with human preferences. For example, in this graph, what we see here is that if we have a base LLM that's just fine, that is just pre-trained, the sensibleness or the safety of the model at each parameter size is much lower than if we start fine-tuning them and bringing in human preferences in the loop. Now, how do we go about this fine-tuning process? So the first stop or the first step for fine-tuning is, again, to do the next token prediction for the model. And in this step, though, we create the fine-tuning, or the data set that we have curated for fine-tuning is curated in a much more careful way. We are not like we're bringing all the data on the internet. Instead, we are bringing in very carefully selected data sets, like large piles of code that we know that they're correct. Hopefully, they're correct and they run well. Large piles of math problem, books that companies pay for, and they bring this high quality data into the model. And to make the model follow the instructions, to make this huge pre-trained model follow the instructions, a part of this fine-tuning process is specifically designed for that, and that is called instruction fine-tuning. And in this step, what happens is that we have designed, or humans, either manually or using templates or using AI itself, they design specific types of data that make the model know how to follow instruction, how to see and read instruction and follow them. For example, here, one instruction fine-tuning data for fine-tuning would be, please answer the following question. What's the boiling point of nitrogen? And then here is an answer. So this is just the model knows, and there's a question, and the model needs to reply. It should reply to that specific question. Chain of thought fine-tuning is another important step in instruction fine-tuning, where the model is actually shown how to follow, like an example with a chain of thought on how to get to have to answer that input example or question and the answer. So the chain of thought fine-tuning is another part of instruction fine-tuning, and let the model to learn and be able to leverage the chain of thought even better at test time, whenever the model is used for testing. And this continues, and there are a lot of different examples of how to solve a coding problem, how to solve a math problem. Although, again, these are not comprehensive for all possible kinds of questions that these models are asked later, but they become much better at following the instructions, at least, that the humans are asking. Now, the way this fine-tuning is done, again, first step was just doing next token prediction on these higher quality data, but also there are methods such as reinforcement learning, fine-tuning, or direct preference optimization, or DPO, that are used to basically bring in more clear reward functions into the process of fine-tuning the LLMs for alignment. For example, let's say we want to fine-tune the model to be better at specificity. We want their answers to be more specific. We don't want them to give general answers. Then our reward function models the specificity, and one way to collect that is to get that from human preferences. So we collect a bunch of data from humans, rating the output of LLMs in pairs, and tell us which one is more specific than the other. And we use that data to create reward models that kind of model human preferences, basically. And then whenever we have a reward model, we can use that to kind of steer the parameters of the LLM through reinforcement learning or DPO, such that they increase that reward model. So that's how we are injecting basically human preferences into the process of fine-tuning LLMs through creating these reward models that follow humans, kind of what humans like to see. Now, so pre-training and fine-tuning has been around for some time now, and what's new, or what kind of really appeared in 2024 was the Inference looking into the inference as a new frontier for scaling and improving language models. So we knew pre-training was good. We knew adding more data even to the fine-tuning process makes them better. But it turns out that we can get even much more capable LLMs by kind of increasing the amount of compute that we kind of throw at them at inference time, which means we are not changing the parameters of the model at this time. So last year, we wrote a paper called Large Language Monkeys. The idea of this paper was very simple. The idea was we can increase compute at inference time for LLMs by just repeated sampling. We just ask the same question over and over again from the same model. Now, the reason this is interesting is that language models have some stochasticity, right? They don't generate the same answer all the time. But it turns out that if we do this repeated sampling and ask the same question over and over again, we get a much more likelihood of getting a correct answer from the model. Given that this is true if we have a verifier that can help us select which one of those generated samples are the correct one. So here is an example of how this works on a bunch of benchmarks. For example, we are seeing it on different types of reasoning across math and coding questions. What these graphs are showing is just the coverage or pass at k, meaning if at least one of the answers in these repeated samples are correct, we give it a score of 1, and then otherwise we don't. So in this case, we're increasing the number of samples per problem from 1, which is the most common way of asking a question from an LLM, up to 4 orders of magnitude, up until 10,000 times. And what we are seeing here is that although a model, like a small model such as Llama 3 8B, does really poorly compared to a model like GPT-4o, which is the dashed red line, as we increase the number of samples in all of these cases, the 8B model does better in terms of the coverage over GPT-4. And these are for really hard coding and math problems. So it seems like the small model already knows how to answer these. It just doesn't output that in the first time that we ask the model. And in September of last year, the O1 reasoning models came out. So this is an interesting graph that by OpenAI that showed as we have train time compute, we know the scaling laws, and we know that this log linear relationship between the accuracy in certain downstream tasks and the train compute. But we can also see the same thing in terms of pass-at-1 accuracy on these O1 models as we increase the test time compute. So this is a very interesting phenomenon all of a sudden, because test time compute, each unit of test time compute is much cheaper, right? It's just running the inference once. So this creates like a new opportunity and possibility to really make the language models powerful. And perhaps we can now tune how much compute we want to add, we want to spend on more or less complex or more or less valuable tasks. Since then, and there's another reasoning model called Gemini Flash Thinking. So the O series and Gemini Flash Thinking both use this test time compute to increase their capability, and they're perhaps trained on incorporating some test time scaling and capability kind of improvement techniques within their training process. So the motivation here is that when we are solving hard problems as humans, we spend more time thinking about them. than when we are solving easier problems, right? We may take a long time before responding. We may take days or weeks, like doing research, like analyzing, running code, like all of that all of what it takes to do projects and solve hard problems. So the idea here is that what if we just bring the same sort of capability to language models and let them think before as they're attempting to solve a problem. And now there are a few properties of these kind of reasoning models. One is that they do problem analysis. When they approach a problem, they first try to analyze what the problem is before just like doing the next token prediction, just responding the first thing they know. They do task decomposition. So it appears that they do break down the question into pieces and different tasks, and then they approach solving them one at a time. Another property is self-evaluation. So the thinking model kind of learn as they're generating responses, and then as they're solving the subtasks, they evaluate themselves and they decide whether they can go forward. Are they doing well so far, or they need to kind of revise themselves? So what comes with self-evaluation is self-correction. They have this ability to recognize and correct their mistakes. Of course, this is like to some extent, right? They're not perfect by any means, but they are trained to have to do these steps and have these kind of properties. And at the same time, they can, now that if they have self-corrected themselves, or if they think they need to try an entirely new approach, they are again trained to come up with new proposals to go after solving a problem if the current approach isn't solving. Here are some examples. For example, the problem here is write a bash script that takes a matrix represented as a string with format this format and prints the transpose in the same format. So the first part is the problem analysis. So the model is basically repeating parts of the question in the beginning and say, let's first understand the input and output. The input is this, which corresponds to this matrix. So it's kind of like breaking, like opening up the problem for itself. And just like as we think ourselves, maybe as humans, when we are approaching a problem, the model is doing that. It's kind of analyzing what the problem is and maybe try to look into an example by itself. And then in this example, the model is doing task decomposition. For example, it breaks down the steps that needs to solve this problem. So at first, it says let's parse the input string to extract the matrix elements, then build the matrix as an array of arrays, transpose the matrix, and then output the transpose matrix in the same format. So this is an example of how the breakdown is done by the model. As you can imagine, for this simple problem, maybe a GPT-4 already could give the correct answer. But for more harder problems, these steps become more and more critical because the opportunity to make mistakes or to just not know how to solve a problem just increases as the problem complexity becomes more. Here is another example of self-correctness that OpenAI put out. Like here, the question is, what is the pH of a 0.1 M solution of NH4F? And with some numerical like definitions for this question that helps the model answer the question. And then in this case, the model says, so let's compute pH is this. And then the model itself interestingly says, wait, the correct formula is this. Like the model is just correcting itself, it seems like, after outputting a wrong formula. And then this is the correct formula, and the model can go and compute and come up with the answer. So reasoning models like O1 but they really shine, at least so far, where we have seen is that in solving reasoning tasks, such as the coding, data analysis, solving math problems, and these are the type of kind of win rate that OpenAI is reporting over the Chat GPT, over the GPT-4o. So whereas in personal writing and editing text might be O1 might not be doing that much better, or maybe even slightly worse than GPT-4o, but it is doing a lot better in the reasoning tasks. And all of that comes at a cost, which is the extra compute cost during test time. Like all of these tokens of reasoning, self-correction, task decomposition, all of that translates to generations, token generations that then translate to compute costs that increases the cost of models such as O1. So with that, I want to hand it to Akanksha.
Thank you, Azalia. So we've heard from Azalia about LLM trends, and we have got large language models and large reasoning models, and that can act as building blocks. So why do we need agents? So we'll take a brief snapshot of why are people excited about agents. It happens to be the buzzword of the year. So let's start by defining what we mean about it in this class. And by no means we are there yet. So this is like an aspirational definition. So what it means to have an agent. So this definition of agents is by no means new. The people who have been reinforcement learning for a long time kind of know that when you have something that can plan the steps of whatever goal it's given, and then interact with the environment and collect some feedback, and then use that feedback to correct itself, that's an agent. That's the reinforcement learning definition. As far as we are concerned, we will have an LLM that will be driving the planning and the execution, and then it will go interact with the environment and then get some feedback. So effectively, it means that you have a chain of LLM calls, but then these LLMs can also direct their own processes, perhaps interact with tools, and then figure out whether they achieve their goals or not. So this kind of mirrors what the large reasoning model was doing, except we might need much more complex workflows. So the reasoning model alone might not achieve it. But you could imagine in the LLM call, what they call as LRM these days, but effectively there might be O1 sitting there, or GPT-4o, or Gemini, or Claude. So you can imagine that any of these could serve as agents. Where we are today and how folks are using agents. So for the intents and purposes of this class, the agentic workflows will also be treated as agents. And what agentic workflows means is that you are basically orchestrating LLM calls with tool use. So tools can be search tools, can be Python interpreter, can be math verifier. So you are orchestrating LLMs and reasoning models with tool calls and code definitions and some form of other blocks so that you can achieve the goal that the model wants to achieve. And you can also be collecting feedback from the environment. So there is two examples that are shown in this figure. On the top left, what you're seeing is that the example where on the left side, the LLM call, that's the generator, is given a goal. It's generating an output. And on the right, there's a evaluation. So it's generating a solution, and then there's the evaluation one. So that's very similar to what Azalia presented as self-correction or self-evaluation. So this is the model as a judge, which is evaluating the first LLM. Perhaps it's better fine-tuned to generate rewards. And then maybe it will say, okay, you generated the correct solution, or that was a bad solution. And then it will come back to give an answer. And when you have the right answer, then that goes to the output. So this is a very simple graph of agentic workflow. Another example that I've shown here is that there's an input, and in parallel gets processed by 3 different LLM calls. So Azalia presented that repeated sampling gives you better output. So this is one very easy way that aggregator can be like, okay, I finally got the correct solution. Or it might be that when you send the solution to different LLMs, they might be fine-tuned in different areas. So they might give you slightly different answers, and that aggregation actually helps you solve the problem by getting different perspectives, which we will see an example of. So all of these are examples of agentic workflows that can be very useful. And typically what Anthropic published in their blog post is that like when we are building these workflows, we can have LLM calls that are orchestrated with verifiers. The verifiers might be deterministic. They might be learned verifiers. Then you can have critics or judges that can, the LLM itself might be trained to be the reward model or the judge, or you might have something that is a human that is judging whether these solutions are better. You can, or a human in the loop to like say, okay, this is a bad solution. You can have tool calls, and you can have even search in the process. So there are different categories of workflows, and I will not go through every one of them, but prompt chaining simply means that you are chaining a whole bunch of LLM calls sequentially. Routing means that you choose which path to take based on the input prompt that you gave. Then you might be parallelizing. So we saw an example of parallelizing where if you have a really complex task, you might actually break it down into independent subtasks, send it to different LLMs, and then get the output. Or you might actually do repeated sampling, like we saw previously. You can also have MapReduce style task, which is called as orchestrator here, where you have one central LLM that is like sending tasks to multiple LLMs that are workers, and then you aggregate things together. And in all of these, you need some form of guarantee of correctness, because otherwise there is really no way to know whether these LLMs are achieving the goal or not. So you need some form of verifier or evaluator or judge, which can be another LLM, which can be a deterministic thing, or it can be whatever benchmark you're driving towards. Like if it's an industry benchmark, they have some norm of what is correct. So in all of these, what's interesting is that to construct these, you need some notion of, for this graph to work out that it's achieving its goal, it needs to start by planning. So if I wanted to get from Gates building to here, I need to start by planning. Like here is my destination, and I need to take this route. So very similarly, the agentic workflows require some sort of planning. Needs some form of multi-step reasoning beyond what the LLMs were doing, where it'd be like, okay, step one, maybe I should try this. Maybe these are the 10 tasks I need to complete to do step one. And then what I'm calling here is self-improvement, but effectively all it means is it needs to be able to say, okay, did I do the right thing? Or ask the environment, or ask some form of feedback, and then be like, okay, did I make progress and get towards this building, or did I go in a completely different direction, right? So those are kind of the new patterns that start to show up in the agentic workflows, which were not specifically there in the earlier LLMs when we were doing instruction tuning, or when we were doing perhaps the fine-tuning for human preferences. And the planning aspect of it really is not solved yet. So here is something that you folks are probably familiar with as software engineers and CS majors at different levels of degree. All of you know how to write code, and the typical process that you will follow is that you will be given a task. Let's say you have a homework assignment in one of your computer science classes, and then you'll figure out which code file you want to go and change the code in, and then you will simply go change the code, and then you will generate the outputs. In this particular case, getting the language model to do the same task is non-trivial. Like it has to go through multiple hoops. So what this figure is showing is that you have a single LLM. It's talking through this agent-computer interface to a computer, and it has basically ability to generate some actions, like it can generate code, and it can get feedback from the computer in terms of like, okay, did it achieve what it was trying to do? So it can start with a very simple example of like, okay, I want to change this particular file and come back with output. We will see example of that in the next slide. So it will generate some commands which will search, navigate the repository, view files, and then edit lines within a given specified file. And then it will look at the computer output, and based on that output, it will replan its next steps. So this is an example of what I'm trying to say. So the model is supposed to, is given a task. It goes and clarifies the user intent. So the first part of this, can we see the mouse? No, okay. I'm gonna try to see if I can, there's the point. Okay, thank you. So, no, okay. Now it's. We're going to have to do without this today. So the first part of what is happening in this coding agent is that from human to interface, you've issued a command and you're trying to figure out what is the human intent of the query. You're clarifying it, you're sending it to the LLM, and then you're refining it possibly. The second part is that once you've understood what the user wants, possibly after refining, then you're making another LLM call to basically search for the relevant files, return the paths of what files you found, and then you keep repeating. Once you found the files that you want to go change, you keep repeating, you generate the right code, and you keep evaluating until the test pass, and then you display output results. So there's like, this is a pretty involved agent in the sense that starting from the human, there's an interface which has a list of actions that it could go act on, and then it has the LLM in the loop, and then it has the environment, which is the computer environment which you're issuing commands to, and then you're seeing, okay, did the test pass? Was the goal achieved in some ways? So this is an example of an AI coding agent. Now, why is this useful? I mean, humans can do these jobs, right? So the reason this is useful is that some of the tasks that we try to do are extremely repetitive. A typical one that our friends at Devin, which is one of the coding agents company, have shown is that code migration. Like if you want to migrate your music repository from Python 2 to Python 3 or something like that, those language migrations are not the most fun job as a software engineer. Or if you have to do code-based restructuring, that's also not as much of a fun job for some of the software engineers. So they find that these repetitive tasks are a really good target for coding agents. It's not a completely solved problem. So like if you look at Sweetbench, none of these are like completely solved problems. Another very good example of repetitive tasks ends up being data engineering. So if you have to do data warehouse migrations, like your data sitting here, you want to wrangle it in certain ways to display a certain set of graph, then doing the extraction, transform, and loading of these kind of data processes can be extremely time-consuming and repetitive. And data cleaning and pre-processing to figure out which column in the data or which sub-word in the data is the one that you want to be dealing with. So these are the kind of tasks that start to get very interesting if you're using LLMs. And I can tell you from experience that like creating tables in LaTeX is one of the hardest things that I do when I write papers. And I have completely offloaded that to LLMs these days. One of the industry use cases that has gained a lot of traction is the customer support agents. And if you look at customer support agents, effectively they can be broken down into, it's an orchestration of LLM calls. So you can call LLMs, you can orchestrate them with external information. So there might be a knowledge base or some tools that you might call. And then they can take actions such as issuing refunds, of course, with a human in the loop to make sure there's enough guardrails. And there are success criteria for these, like what goal they're trying to achieve is the user resolution. These can also get annoying if they don't do the right thing. But here is an example of what's really useful in the existing customer agent workflows is that if you do live transcription, so you transcribe what the agent is talking to you. So this is an assisted workflow for customer support. And then let's say you're talking to a customer service agent and then they need to look up, instead of having to like click on 5 different databases to find all the information, they just issue the relevant LLM calls and get the knowledge assistance. And then as long as it's grounded well enough, they can very quickly get the output to you without putting you on hold for 3 minutes while they go look up these knowledge bases. And then once they come up with like, okay, your resolution needs to be like, these are your options, and you select an option, they don't have to like click on another window. Perhaps they can just issue the right command to this interface, which is your agent, the customer support agent. And at the end of the call, the company that is supporting you in this customer support wants some summary. The LLM can summarize what the workflow was, what all it tried, and that's a pretty good way to do quality assurance for customer support. So that's kind of gives you a sense of why these things are useful. And some of the ones that are useful to perhaps researchers in the room and useful to me personally are like if you're trying to understand complex topics and say provide findings in a comprehensive report, the LLMs can be super helpful. Now, this also means that all the undergrads who are asked to write papers, they can use LLMs. So if you build this agent, they just be using LLMs. But what makes this agent hard is that if you just use direct prompting and tell it to go write an essay, it will not be grounded. That's one problem, but it will also not have multiple perspectives. So what this particular paper proposes is that if you're trying to write, say, Wikipedia level summary articles from scratch for a given topic, you have a pre-writing stage. So it will go consult a whole bunch of references, cover diverse perspectives in researching a given topic. It will even come up with an outline. It will ask different questions, assuming these different perspectives, and then combine all of them and synthesize all of them into a full-length article. So it becomes, if you go back to our prompt chaining example, this becomes more of a prompt chaining example with like multiple tool calls in between, as opposed to a single LLM call that can have solved the entire workflow. So this is a pretty useful workflow for, say, generating reports. Now, combine that with the coding example. So here in this figure, we have this complex problem where you're trying to solve there is the zeroth order optimizer called Meze, and you're trying to train with this new optimizer on this data set that you have stored in your Google Drive, and you're following the code from some GitHub repository. You can actually build agents that can do these tasks these days. The first step you will do is, of course, you will figure out how to get it to set up the configurations. So the left side in the figure shows up all the steps that the model is taking to set up the configurations. Then, of course, not everything works because GitHub repositories don't work out of the box. So then it has to go resolve some dependencies, which is the first step on the right. And then it can also, once it has running code, then it can get the metrics and then report the accuracy for these things. So what this roughly means is that it's possible to interweave these coding tasks and these instruction following tasks in useful ways to like execute some known workflows. And for this kind of agent to work, it basically needs to have sufficient instructions on like where to look for data, what does it mean to understand that data, where to look for code, what are the instructions, what are the dependencies, what are the configuration files that needed to work in this repository, and then once it figures out the commands to run these things. So you can imagine that there would be a few different set of tools that need to work well with this LLM to complete this kind of workflow. And this is one of the papers that I will not cover in detail, but it's one of the famous papers called the AI Scientist. So it basically covers the idea of like, you can use LLMs to brainstorm a set of ideas and then do experiments on those ideas possibly. And then it can even write the paper. So if we look at the last two slides, we were doing some sort of experiment integration and paper write-up. So now if you combine all of that with idea generation, then who needs scientists these days? But that's not really true. Like, you need scientists to really help guide the process, but it can really amplify your productivity to the point where late December, right before Christmas, there was an article in New York Times which said that AI hallucinations might actually help science dream up big breakthroughs. And one of the interesting things that they were talking about, which also shows up in a very interesting paper called RE Bench, but what they're basically saying is that when you have a particular subject and you're using the LLM to brainstorm about it, it might come up with perspectives that you haven't really thought through because it has this instant access to the knowledge base. And that can somehow like help the scientists dream up new ideas, which sometimes you might not have seen in some ways. And in my personal explorations in just the field of ML, like asking you to explain concepts in 5 different ways sometimes does help come up with new ideas. In this particular case in science, folks believed that they were seeing new structures for proteins, or in chemistry, they were seeing new things. So it's really something interesting to think about. Okay, so with that introduction, what all are we going to cover in this class? So we're going to start with test time compute scaling. And Then we're going to look through self-improvement techniques, which are going to be based on, say, verifiers, feedback, reinforcement learning, or search. Then we're also going to cover how to integrate tool use and actions with LLMs, or how to integrate retrieval and memory with LLMs. Then we're going to look at how do you get, say, vision as a modality, so multimodal, like the computer screens as a modality to integrate with LLM calls. Then we will have a lecture on planning and multi-step reasoning. And then we will have a lecture that covers across different agents like evaluation benchmarks. And then we will cover some futuristic topics, including multi-agent systems. And throughout the course, say after every 4 or 5 lectures, there is guest lectures on AI scientists, AI coding agents, multimodal agents, and AI orchestration frameworks. And the course schedule is up on the website. We have put up a preliminary list of the paper readings for each of the topics that I just mentioned, and also the due dates for assignments. There are 2 homework assignments. I'll cover these logistics shortly, and the project, etc. But all of these details are up on the course website, so you can check that part out. So before I move to course logistics, are there any burning questions? Okay. I don't see a hand. Yes.
I guess for the projects, would this be something like entirely self-driven, or will you have like some ideas?
Great question. We will have ideas, and that's the next part of my slides. So we'll go to that. Any other questions? Yes.
I guess I'm curious, out of the different areas that you covered for like verifiers, generators, blockchaining, all these different things. I'm curious what you think are the most promising and the most, or the topics that are getting the most attention right now, especially given that this is kind of extremely topical at the moment. Where do you think the most promise is in some of the materials that you've shared?
I think we should save that question for the last class after the projects, because what you'll find is that what is happening is that people are building, because this is so new, people are learning as they go, so they are building however they can, and then they are hill climbing on whatever they think is the right benchmark. Often the question really is not what is the right workflow. The question often ends up becoming, you have the right eval benchmark to even measure what I'm measuring, right? So at the end of the day, you start with the simplest, and then you figure out whether you're measuring the right thing, and then you hill climb from there. That's the most practical industry answer that you'll get. Of course, the different papers will propose different things. Given that Anthropic published it, all of them are patterns that they're seeing. Okay, so going through course logistics. So I think this slide I covered. So in terms of logistics, all of you made it to this room. So it's in building 260 in this room. Mondays and Fridays, this is the time, 1:30 to 2:50 p.m. In terms of prerequisites, we went with 229S, 224N, and Python and NumPy. And we also assumed that the people who were admitted to the course have research experience. This is the first iteration of the course, so we were not able to admit. We had 150 plus applications for this course, and we were not able to admit everyone. So since course projects is a big part of the course, we did assume that research experience is required this time. In future iterations of the course, that might not be the assumption, but thank you for joining the course. A lot of the value that you'll get out of the course is going to be in class participation, because the research papers that we are discussing are like literally published in the last 1 year, perhaps more recent papers. So it's the discussion that you do, the discussion questions that you submit that will really drive your learning. It's not that we are experts on this alone, like we are all driving this wheel together. The homework assignments will do our best to make sure that you develop intuition for the basics, and then the project will really help you understand and iterate through kind of questions that was asked just now about like which approach is the best. Well, I don't know the answer off the top of my head. For different benchmarks, different approaches might work better. So I think how you go through the research methodology that you develop, the eval benchmarks that you use, all of those are going to really help you maximize your learning. Sorry, this is a repeated slide. So what we have planned for this class is, so the next lecture, Azalia and I will deliver, which is the test time compute scaling. But in the subsequent lectures, we expect the students to form groups of 2 and present one paper in groups of 2. So there will be like 6 students presenting per class. So each paper is presented by 2 students in 15 minutes, followed by 10-minute question and answer format. That's what we have planned right now. And you can indicate on Canvas which week you are able to present. Your grading credit for that in-class presentation, there will be 3 groups presenting in any given class. The grading credit is 15% for that in-class presentation, so please sign up. That's not all on you. You can come to our office hours or request feedback over Ed, show us your presentation or whatever points that presenting team is struggling with in understanding that paper.
Yes.
Do you want to add something?
No, I think the next slide is.
And upload your presentation in Canvas for that corresponding lecture. And this is an example of in Canvas, if you go to the People tab and you go to Groups. So this is for the paper presentations. You will see that there's a lecture date. And if you're available, please choose early on that which lecture you'll be able to present. Otherwise, there will be random assignment, which no one likes, or I'll be calling out on people. So please figure out which lecture you're able to present.
And it's the
first come, first serve right now.
And ideally, you would want to learn about all of these papers and all of, so don't worry if you don't get your first set. We have chosen the papers in a way that is, hopefully it's very readable for all of you and you can present any of them, but you need to spend the time to like really understand the paper, and we are here to help you if you have questions about them. But you need to sign up here.
Yes.
Are we only supposed to do one?
Yes.
Paper?
Yes. There will be discussion questions that have lower points, but that you're supposed to do every one of them. But the presentation is only 1 paper per quarter. What will you present? So I think we're trying to model it next week, but it's basically as if you were the author or the critique, the reviewer of that paper. You will present what was the problem statement, what was the motivation and background of why these folks chose to present this, try to solve this problem. What are the new ideas and contributions in this paper? What is, say, the experimental methodology? What kind of experiments did they run? What are the strengths and weaknesses? And also some what-if questions of like, what should have changed for this experiment to be done better? Should they have tried a completely different technique? So thinking about like, what should have been different in this paper to get, say, better results, or these results might not be valid. Like, what are the assumptions that are worth questioning? Do you want to add anything?
Yeah, I just like, so we have spent a bunch of time finding papers that are most like relevant and comprehensive and that kind of cover the space as much as possible. As you know, this field is really developing, right? Every day there might be new papers. So while your task is to read that paper and present, of course, we would love to see your kind of like critique of the paper, or you say, oh, there's this other paper came out more recently and it's doing like things very differently and it's better, or it's like this led to this other even newer kind of approach that came out last week. So we really hope to see that more kind of like that your presentation is very engaging and not only presents the paper but also has like some like accounts of some what ifs and some like what this paper led to. Although we don't need you to kind of like completely criticize it. Like the papers we chose actually are good papers, but we kind of expect like a deep dive into the paper and maybe around the topic of the paper presentation.
And you can reach out to both both of us and the TAs to discuss things. If you are needing some feedback or help or want to discuss it more, but like we are hoping that you can engage and learn more. And then where your classmates will help you is that every student presentation will be followed by discussion. So for this discussion period, we are hoping that everyone gets to submit 2 questions for each of the student lectures. You're welcome to submit it for the guest lectures as well, but those are not graded. For the student lectures, we expect you to submit it, and you get 1 point for each of the lectures. So there's 10 student lectures, 1 point per lecture, 2 questions. You can choose 1 reading out of 3 readings or 2 readings out of 3 readings, or you can submit more questions. But to get that 1 point, you can basically submit 2 questions. That is what we are expecting. Questions on this? Is that something that anyone has opinions on? Yes.
Where do you sign up for the student presentations?
It's in Canvas.
Okay.
I showed the tab here. In Canvas, if you go in Canvas, under people, under groups, and then you go class paper presentation groups. Did you find it?
Yeah.
Okay. And for the second lecture, which Azalia and I are presenting, the grade scope submission for submitting weekly discussion questions is up. So read at least one of the papers and submit some discussion questions. There are obvious ways to cheat by using LLMs. I'm quite aware, since this is a class on LLMs. It's really your owner code and your learning to think about the papers. So if you submit it using LLMs, that is completely up to you, but it might not be very beneficial to you.
Well, and it doesn't follow the honor code, which this class is part of. So, and then the reason we really put these questions to be asked is that sometimes this is a graduate level course, right? And it's project based. We do not have homework for every topic that we cover, but it's important. Like if you really want to learn from this course, it's important that you're like really understand every topic that we cover. And the point of these questions is that even though you're not presenting, you're just coming here and listening, but you can engage because you have read at least one of the papers and you have tried to think about it to come up with questions about that. So that's the entire point of doing that, to just make everyone more engaged.
There was another question here. Go ahead.
On Gradescope, I see the assignment, but I guess is it just not open this week?
That's a good question. It should be open.
We'll look into this.
Clickable. I don't know.
Okay.
We'll look into it. Has anyone else?
If it's not clickable, then I will check right after the course. Thank you for pointing that out. Okay, so apart from the student lectures, which is and the weekly lecture thing, you have 2 homework assignments and 1 course project. The 2 homework assignments are basically to help you build intuition on the self-improvement techniques and the multi-hop reasoning techniques. So one of them will be out on January 24th. By that time, you will have submitted your project proposal. So over the next 3 weeks, think about the project and what you might want to do and who you want to work with. And then we will have the homework 1 out, which was due on February 3. So you'll have 10 days to submit this. And the second will be due on February 14th. It will come out on February 3. And then the second half of the course is very focused on like just the project aspect of things, and there will be a bunch of guest lectures. So at that point, we expect you, once the second homework is done, to completely focus on projects and present. There will be midterm presentations, but there will also be like the final presentation. So that has the most amount of credit for you to do well. You will propose the idea. We will provide inspiration